So here we're going to take another look at partition or distribution coefficients, and we are going to look at the partitioning of, let's say, cobalt between a metal phase and silicate. Now, by silicate, we might mean a collection of silicate materials that could represent the Earth's mantle. So in this application here, we know that the Earth's core is an iron-nickel alloy. We know that from looking at meteorites and also from seismic data. And then we have a mantle that's made up of all kinds of silicate materials. At the top of the mantle, we have olivine and pyroxene and garnet. At the bottom of the mantle, these turn into perovskite or post-perovskite phases. It doesn't really matter. What we're going to do is do some experiments to try to figure out what the concentration of cobalt would be. We cannot drill down to the core and sample it directly, but there are bits in the mantle that do come up to the surface. So let's take this partition coefficient and first again look at its definition. By definition, this would be the concentration of cobalt in whatever this upper phase indicator is. So we have metal, and then we have the concentration of cobalt in a silicate phase. So usually the tradition or the habit is that this ratio matches this ratio over here in the superscript. We can abbreviate that a little bit, maybe just for the rest of this video, we'll just call it MET for metal and SIL for silicate. And if we do some experiments where we let silicate minerals equilibrate with an iron-nickel alloy and we dump some cobalt into that mixture, we might find out that the partition coefficient or the distribution coefficient is equal to 24. So we know this from experiment. So what can we do with that? Well, let's say we analyze a chunk of the mantle over here, and we find out that the concentration of the silicate mantle is equal to, I don't know, pick something like 105 ppm. And that's not entirely arbitrary. That's from a paper by McDonough and Son where they estimate the composition of the Earth's mantle. So what we can do is now use this observed value of 105 ppm and this observed experimental result to try to calculate how much cobalt we would find in the core. So what would be the concentration of cobalt? Let's write that a little bit better. C subscript CO in the metallic core is equal to what? Well, it's going to be this thing here, the top of the ratio. So this value of 24 here is equal to the concentration of cobalt in the metal phase divided by the concentration of the silicate. We know that. We've analyzed a piece of the mantle, and it's 105 ppm or so, we think. And so the concentration of cobalt in the metallic core would be the product of these two numbers, and that would give us a value of 2,520 ppm. And so this would be the concentration of cobalt in the metallic core. Now that is valid. This concentration is valid only to the extent that our experiments are valid and to the extent that our estimate of 105 ppm really does represent the mantle on the whole. So there are ways of making errors, ways of making very large errors. Maybe the distribution coefficient changes as a function of temperature or pressure that throws it away from a value of 24. Or maybe we're taking a non-arbitrary part of the mantle, and maybe the entire mantle really is not 105 ppm. But if we do a number of experiments and are very careful about how we analyze the mantle, we could start exploring the value for a planetary core by these kinds of partitioning experiments and calculations.